All right, I want to quick walk through this logistic function project and what it might look like for you. I'm using the same rubric that I've used in years past that we're going to modify a little bit. Right? You don't need to follow this step by step. It doesn't need to be an answer key on a separate sheet of paper. You don't need to hit every single one of these bullet points, but it's a good guideline for what to follow along here. But yeah, the whole idea is I want you to try to come up with something that would be modeled theoretically by a logistic function that kind of follows this pattern that looks like it's increasing at an increasing rate at the start, that exponential growth to begin with, but eventually will taper off and hit some ceiling here. So you got to kind of be careful. Some functions grow rapidly right at the beginning, kind of would balloon out of there and then kind of slowly maybe taper off. You want something that is increasing exponentially to begin with and then slowly tapering off there. Yeah. So try to come up with some situation, include a little backstory on the situation, a partial table of values. You don't need the full 60 thing piece table here like I have. Just a little partial table of values. Look at the book. Questions 3 and 5 in section 7-7 are excellent questions that just have 5 or 7 data points to use. And then I want you to kind of think of yourself as a teacher and you're asking some questions about asking somebody else to interpret that graph and that function. So it says at the minimum your test questions should include finding an equation from the given data. That's probably the most important mathematical part, Can you pick 2 points from the data and find the equation of that? And I went over how to do that in the last video, that introduction to logistic functions video. We looked at 2 examples, and I will put up the answer keys to questions 3 and 5 as well. That will give you 2 more examples on how do you find the equation for that. You should include a graph of the function in a reasonable window. Just make sure that you're not using a default 10 to 10. That's probably not going to give you anything, So just make sure that you're looking at it where you can kind of see the whole big picture of that. Finding the output for a specific input is just saying, hey, use the situation and use the pieces in there to try to kind of figure out, hey, this was the model that we used for this, g of x was this, and I found this equation in that last video. And so a question that you might ask is say, hey, how many coronavirus cases were there on March 30th according to this model? Well, March 30th would be the 30th day of this example when x would be equal to 30, So to find that, all you'd have to do is, what is g of 30? And it would say, there's 4,010 cases on March 30th according to our model, With this, I have the actual data that says, on March 30, there were 4,250. So another question that you might ask is, how close is this to the actual data, and maybe what's a rationale for why, So this would say, the actual data was greater than this projected data, So yeah, there are more cases than what the model actually showed using these dates. Why? I'm not exactly sure, but maybe there's some explanation for that you could think of if you had more time. Another question, the second piece in here says, find the input for a specific output y. That's a lot harder to do algebraically. This you could just plug in 30 into here, and you could actually show get the output for that. But graphically, that's all I want you to do, So if you said, hey, how many days does it take from March 1st until they hit 6,000 cases according to the model, All you have to do is type in y equals 6,000. Say, hey, according to this logistic model, it's going to be after 37 days, or on April 6th is when they should hit 6,000 cases. And in actuality, they hit 6,000 cases on whatever, I don't know, somewhere around there between day 39 and 40, So it's pretty close, The last part is one of the most interesting ones in here that says, asking for the point of inflection and some meaning of the context of the situation. The point of inflection is where it stops curving upwards and starts curving downwards, where it stops increasing at an increasing rate and it's still increasing, We still have more cases going, but it's at a decreasing rate. The number of cases is getting less and less every time. And for these logistic functions, it is always halfway between the bottom and the top. All right, so if this is right between 0 and 6800, the point of inflection of this is going to be halfway between or at 3400. So if I did this, right, it says the point of inflection should be around March 28th. Coincidentally, March 29th is when all of Australia went on like official lockdown, like the whole federal thing. So that's about right. The point of inflection is where they started to implement some measures to try to curb this thing, right? And the data actually shows like, hey, that's pretty close. March 28, 29 is when it says this. So my model seems to be pretty good. Right? Another way to think about this, that point of inflection is it's where the rate of change is the greatest, right? It's the steepest curve right there. We have the most cases per day right there. I made my function be g of x. If you want to find the rate of change of something, and this is some good calculus practice, the rate of change of something is always called the derivative of it. And you can find it by doing g, what they call prime. It's just a little single tick mark, the single quotation mark. And if I have g of x defined, I can find g prime of x, this rate of change, which basically tells me how many new cases were there per day, right? According to my model, on March 24, there would have been 303 cases in that day. And on March 28, right, that was where the greatest rate of change was, right? That right there would have been about 386 cases per day. And you can kind of look at this, right? Here was the actual data here, right? The daily new cases. Yeah, right. Like it's not a perfect curve. There were some, right. I think these are like on Tuesdays is when they usually have like the greatest count. But in that range, somewhere between there, right? March 27, 28, 29, right? That was where that thing peaked before it started to come back down, right? So that point of inflection is always at the top of that curve. If it was a perfect curve, that model, that would be there. And it's where this stops increasing at an increasing rate, it starts increasing at a decreasing rate, and there's usually something that's going on there, right? Something that's happening in that. So, yeah. Again, get creative. You can do lots of different things. There are a ton of different graphs that look kind of like this. I have a few different notes over here, right? When you're finding the equation, right, that 0.1, finding the equation of the data, you can't actually use the 0 or the max, right? That doesn't actually work graphically. Those are supposed to be asymptotes. So even if in the real world, right, something does exist at 0, there were at one point in time 0 coronavirus cases, right? You can't use that data point. You have to use like 1, right? And you can't use the top either. That also should be an asymptote. It's never theoretically getting there, right? This is just a model, trying to model the real world. It's not dead on, right? You can have a decreasing example. It doesn't have to be an increasing logistic function. You could have something that was maybe decreasing, getting closer and closer to 0, right? The math is the exact same. You just end up with a b value that's less than 1, between 0 and 1. Make sure you check your equation in Desmos. It should actually go through the points you specify. So if I go into here, right, in Desmos, I use points 14, 248, and 35, 552. And so I should make sure that my green function here, that at 14, right, it is actually going through that point, that 248. Right? I could find like what is g of 14, and it's 248 and a half. That's close enough, right? I rounded some of these numbers here. If I went out to a few more decimal points, it would probably give me exactly right on. And g of 35 better be close to 5552. Right, a little bit off again, just due to some rounding errors. In the grand scheme of things, that's like less than a 0.1% off. Right, 5 out of 5,000. So, right. But yeah, if this was like 6,000 or something like that, like maybe some math is not quite right. And if I did exact values here, if I went out to a few more decimal points there in the A and B values, it would get closer to being dead on. Yeah. This is a little interesting one that I'll actually talk about a little bit more when I talk about the mayhem So I'll kind of leave that. You can read it there. You can do ones that don't have 0. It's just a little bit more mathematically challenging. But yeah, use the examples in the textbook. One note, I will put up solutions to that. Yeah, that should help you in your quest. So, quick jump cut addendum to the end of that last video. One thing I should talk about is that C value. Right, you have to create the equation using 2 points, and one thing that you do need to do is kind of decide upon what the best C value, top value is for your logistic function. In mine, I kind of looked at my data. It said, hey, 6,800 seems to be a reasonable estimate for the best data here. And so it was just kind of an arbitrary thing on my part. If you're using Desmos to come up with your equation, which, again, if you're going into like AP Calc, I would really encourage you to try to do this algebraically at least once for your project, because it's really good practice, right? Just that algebraic manipulation skills. But if you want to focus a little bit more on the research, the project itself, Desmos can actually give you its best guessed C value if you just put it in as a letter, right? A, B, and C. Desmos will, if you use that tilde symbol, it will give you that approximate all of them, right? To make this number be the highest, right? Give the error the lowest. I didn't do that in this because it gives me a C value, an upper bound of 6,600, even though my data is actually going above that, right? Because at the end of this, it's not really behaving purely logistically, right? A logistic function, if I'm looking at it, right, it should have a pretty specific like bell curve set to it, right, where it's going up, it hits some peak, and then the back side of it behaves exactly like it did at the front. But that's not really what's happening in this case. If I actually look at the data here, right, the tail is a little bit bigger on the right side than it is on the left side, right? So this thing is increasing a little bit, maybe more linearly towards the end. It's not really hitting some asymptote. Because again, this is just a model. It's not exactly a perfect piece. So, right, this is actually going past 6,800. It's going to 6,849. I just kind of, with this data, made that 6,800 because, yeah, it kind of seemed what it would maybe be approaching. So, again, if you're making your equation, you just have to decide upon that. Or if you're going to let Desmos do it for you, go for it. That totally works. And maybe you could, right, talk a little bit about like, hey, this is what Desmos thinks is the best, and this is where the theoretical consideration should be, and what's the differences between there. Again, go into as much depth as you want with that.